This is step 2, question number 8, 2009. It's also question 3 from the vectors step 2 support module. So we have 3 points A, B, and C, which look maybe like this. And P and Q have position vectors this and this. So P is, and lambda is between 0 and 1. So this is some small amount of A, so maybe like this far of A, plus, and then 1 minus lambda is also between 0 and 1 if you do the maths. So plus some small amount of B. B goes in this direction, so parallel to that, some small amount of this in this direction, maybe takes us to roughly here, and we end up with P. Now, there's something important that we need to realize about P, which is that it very specifically lies on the line B to A. And the reason it does that is because if you group this, not in terms of A's and B's, but in terms of lambdas and non-lambdas, it looks like this. And now we have an alternate description of P, which is to do all of B, so you just travel to B, all of B, and then some small amount of A minus B. Now, what's A minus B? That's minus B plus A. That's the vector B to A. So therefore, P must lie on this line somewhere because it's all of B plus some amount of that vector there. So P is somewhere on this line. Very similar for Q. It's some amount of A, where that some amount is actually a big number, bigger than 1. So you do quite a large amount of A, plus some number, and now this is a negative number, so you have to go backwards, opposite direction of C, backwards like this to Q. And likewise, Q actually lies on this line here, C to A, because if you do the maths and rearrange for mu's and non-mu's, you get this. So it's all of C plus some big amount of the vector A to C, or C to A. So it's a bit like this here. And you end up with Q over there. Given that this times this is this times this, now this messed me up for a long time. C to Q is not, I just said it out loud again, this is not C to Q. This is not the vector C to Q. This is the distance C to Q. There's no vector symbol here. So this is not the cross product. This is just the distance C to Q times the distance P to B, and so on. Right? That messed me up for a long time. So C to Q, I just said, was, well, that's the distance A to C times by mu. That's what we just kind of said before. And B to P, well, that's just the distance B to A times by lambda, as we said before, as we were talking about before, with to do with like P being B plus lambda amounts of this vector. So therefore, it's just lambda of the distance to get to this. And now we can just replace those with there. And this isn't anything to do with cross product. You just factorize out the lambda and the mu, and you cancel these things immediately. And you end up, or you write it again for no reason. Well, of course, C to A, because their distances is the same as A to C, and then you cancel it. But yeah, sure, obviously, it's just lambda mu equals 1. That messed me up for a long time trying to get that to work, and it just wouldn't, because I was thinking of these as vectors. But yeah, they're definitely not. Okay, find mu in terms of lambda. We just did that, sorry. And now, show for all values of lambda, P to Q, the line P to Q, which is this line here, passes through a point D that satisfies this. So, okay, P to Q. Now, the line P to Q is, well, let's just do this normal 3D vector style. You go to P, and then you do some amount, we'll have to invent a variable, of the vector P to Q. And that will get you anywhere on this line here that goes through P and Q. So P to Q, the line is you go to P, and then some amount, I'll just call it K, of Q minus P. And that will describe the entire line here, going through those 2 points. But okay, we have expressions for P and we have expressions for Q. After I did this, I realized that maybe this way might have been easier to write it like this, but it doesn't really matter. We're just going to group everything for A, group everything for B, and group everything for C, which will look a bit like this. And then we just said on the previous slide that mu is 1 over lambda. So we'll replace all of the mu's in this case with 1 over lambdas. There's only a couple of them. We'll replace those with 1 over lambdas. And this is the line P to Q in form A, B, and C. And now what do we know about this? Well, D, this point that exists on PQ, has to have A coefficient of -1, B coefficient of 1, and C coefficient of 1. So we look at these and we think, well, what's the easiest one to deal with first? This one looks very easy for me to rearrange. So I can just set that equal to 1 maybe. And my aim is to rearrange this for K maybe, which seems easy. I'll just move this whole object over here, take away 1, which cancels with this one, and you just get minus lambda over this is equal to K. And now if you put that K into your other 2 results, so this whole thing, if I put this K into here, I need that to equal 1 for D to actually work. So let's put this value of K into here. This works out quite nicely because this becomes lambda minus lambda, lambda over lambda, minus 1 over lambda is just this, and then this cancels with this, and also cancels with the negative, and this lambda cancels with this lambda, and you just get 1 equals 1. So if the B coefficient is satisfied, that implies and means that the C coefficient is also satisfied, and now we'll just check the A coefficient, which is the most annoying one to do, but this goes down here, you cancel the 2 lambdas, you put the minus there, you can put a plus here if you want to, and expand that lambda into there. Here, I just said this was plus lambda squared minus 1 at the top, and this is nice because this is a difference between squares, which will cancel this down as long as you also cancel a negative right there. We're aiming for this to be minus 1, of course, and modulo it is of course minus 1. So this is all satisfied as long as long as one of them is. So it's all nice and consistent, and we're all good. What can be said about the quadrilateral ABCD? Well, when you're asked quadrilateral questions, basically it's what type of quadrilateral is it? That's the question, isn't it? So is it a parallelogram, a trapezium, a kite, whatever? And like the easiest thing to think about is parallelograms. They just have two pairs of parallel sides, and parallelness is the thing that you do a lot in vectors. So that seems the obvious one to start considering. So how can we, based on what we've just learned about D, which is the final position in this quadrilateral, can we point to any parallel stuff here? And if you just rejig this slightly, because of course when you're doing vectors, it's all about, this is the vector C to A, it's A minus C. So can we get some more minuses here? We've got a B minus A there, and so we've got a D minus C if you just bring that C over. And so this is the vector C to D, and this is the vector A to B. But of course, if you're labeling your parallelogram like A, B, C, D, that means the opposite two sides are now not only parallel, but they're also equal in length. And so if the opposite sides of quadrilateral are parallel equal length, that means that the other two sides are as well, and means it's a parallelogram. It's also technically, I would say, a trapezium, but a parallelogram is kind of what they're looking for here. And thanks for watching.